I'd like to show you a couple of examples from this stoichiometry practice problem worksheet. So that way, if you have questions, you can look through this video and then make sure that you're doing the right thing. So the first problem, pentane is burning in the presence of oxygen to produce carbon dioxide and water. This is a combustion reaction, and you need to balance this reaction. That should be the first step all the time. So oxygen is giving you CO2 and water. If you balance this out, you will see that you need 8 oxygen here, 5 and 6. What this tells you when you balance it out, it tells you molar ratio. It gives you the relationship between pentane and oxygen in terms of their mole. So every mole, 1 mole of pentane requires 8 moles of oxygen. You can say that with other things that are present here. So every 8 moles of oxygen, you can say that you produce 5 moles of carbon dioxide. So you're using that sort of relationship to solve this problem. So you're given 3 moles of pentane, and you have to find moles of each of the product. So using the molar ratio, you can go from moles of any of these guys here to any of the other guys that are present in this reaction. So if you start with 3 moles of C5H12, you're trying to get to moles of CO2, and obviously you want to get rid of moles of C5H12, so you want to put it on the bottom, so that way these units will cancel out and you will end up with CO2, moles of CO2. So you have to look at the coefficient. If you do that, you know that 5 moles of CO2 is being produced for every 1 mole of C5H12 that's present. So the rest of it is just carrying out the math. If you do that, you end up with 15 moles of CO2. And you do the same thing when you try to find the moles of H2O that's being produced. So you start with 3 moles of 3.0. I'm sorry. We should stick with the significant figures that they give you. 3.0 moles of C5H12 that's given, and molar ratio is every 1 mole of C5H12 you get 6 moles of H2O, and these units cancel out and you end up with 18 moles of H2O. And the rest of it is checking the significant figures. You always go with the small number of significant figure. In this case, you only have 1 number that has 2 sig figs, so your answer should be given in 2 significant figures. So 15 is okay and 18 is okay here. Number 3 deals with the same reaction, so we can use a molar ratio that's found in this balance equation, but the only difference is it starts off with the grams. So you start off with 245 grams of pentane, and you're asked to find how many grams of oxygen that's needed to react with this many number of grams of pentane. So if you go carry out the calculation, you cannot go directly from grams of pentane to grams of oxygen, but what you can do is use the molar ratio relationship. You can go from the pentane to oxygen. So what that involves is you have to start with grams of C5H12, then go to moles of C5H12. Only then you can use the molar ratio relationship from the balance equation to go to moles of oxygen, which allows you to go to grams of oxygen. So how I look at this is like, if you are from Chicago, you have different lines of CTA that you can take. So let's say this is blue line, this is red line. So we can call this grams of A and grams of B. So to go from this location to this location, you cannot go directly, but you need to go through is go to Chicago Loop and exchange the train. So if you're taking blue line, you have to go to the Chicago Loop and exchange the train over to B, and then you can go to grams of B. So loop is more like a mole here. Loop allows you to go from moles of A to B. Once you switch over, then you can use the molar mass to get to grams of B. I hope that made sense. And to get to moles of A to moles of B, that's when you use the balance equation. Look at the coefficient, look at the molar ratio from that. So if you carry out this calculation, the first place that you want to get to again is moles of C5H12, and you want to get rid of grams of C5H12. If you actually use the periodic table and carry out the math, you will see that every 1 mole of pentane has a mass of 72.17 gram. So I know you have done many calculations like that. All you're doing is look at the periodic table, molar mass for carbon, multiply that by 5. Same goes for hydrogen, multiply that by 12, and you're adding the whole thing, and you end up with 72.17 gram. So you know that grams of pentane canceled out and you're at the mole, and which means you're at the Chicago loop, and you can switch over to any of the moles in this equation. So the moles that we want to switch over to is moles of oxygen, and you want to get rid of moles of C5H12, and you use the balance equation. So if you look at the coefficient, you're using this one, so 8 mole and 1 mole. So every 1 mole of pentane you produce 8 moles of oxygen. So moles and moles of pentane cancels out, and you're at the moles of oxygen. The final step is going from moles of oxygen to grams of oxygen. So every 1 mole of oxygen has a mass of 32.00. If you look at single oxygen from the periodic table, it has a molar mass of 15.999. So you need to double that because oxygen gas is a diatomic element. So if you carry out the math, you end up with 868 grams of oxygen, and the final step is checking the significant figures. If you count this, you have 3 sig fig, and this one has 4, and this one has 4. So you have to go with the lowest number of significant figure, which is 3. Do we have 3? Yes, we have 3. So this answer as 868 is correct.